Probably assess that tomorrow. But so what we've been doing is sort of pursuing different lines of evidence for evolution: fossils, structures in living things, and then molecular evidence. We'll get more into molecular evidence later when we get into cladograms. But let's shift gears a little and start talking about the genetic basis of evolution and how it affects the gene pool. Because remember, natural selection, that's the environment acting on, what was it again? Good, phenotypes, but evolution by natural selection is a shift in allele frequency. And so, okay, we can talk about the gene pool, which is every allele for every gene in a particular population. That's the gene pool, constantly changing. And in any gene pool, for any particular gene, the alleles exist at a frequency. You can express that most commonly as a percentage. And so, not to beat the rabbit example to death, but let's say it's as simple as long hair is dominant to short hair in rabbits. And let's say that those allele frequencies in a particular rabbit population are at 50-50, that it's 50% big H, 50% little h. Can you tell me anything about what that rabbit population looks like?
Mostly have long hair, probably.
Do you think they mostly have long hair? Why do you think that? Because big H is dominant, and if half of the alleles are big H's, it's a pretty good bet that more of them have long hair. I mean, is it possible that half of them have long hair and half have short hair? Yeah, it's just not likely. They'd have to all be homozygous dominant and all be homozygous recessive, and then you could have 50-50 long-haired and short-haired rabbits. More likely, it's probably something like 3/4 of them have long hair. That's not the important part. It's not important to know how they look. It's important to know how those numbers are going to change as the environment changes, right? So as long as you know what's going to happen to those frequencies over the years between the generations, remember, it's not just the rabbits going, it's cold out here, long hair. They don't do that. Individuals can't evolve. But if the climate does get colder over the next 100 years, what is the likely thing you're going to see happen to those numbers? Eli, what is the likely thing you're going to see happen to those numbers if it gets colder over the next 100 years? So this number, the big H number, you say that's going to go up. How about this one? Necessarily, it's going to go down, right? It's a proportion, so a percentage. Yeah, that's it. It's the evolution itself is a change in those numbers that represent allele frequency. That's the evolution part. But to take that a step further now. Oh, and we should probably write that down again, just because the state test loves it. Evolution is a change in allele frequency. You're going to see that somewhere. What's cool is you know enough about genetics at this point that we can start to explore what natural selection looks like in a gene pool. So most traits, it turns out, are polygenic. Remember that? No? All right. Remember graphing human height? We said that, the average is probably about 5'7", 5'6", and then it's going to go down on either side of that to create that bell curve type thing, which is so common in real life that statisticians call it the normal distribution. It's the normal distribution of most genetic traits as well. So what's cool is knowing this. Of course, it makes it really hard to do genetics problems when it's a polygenic trait, but it makes it really easy to look at the effects of natural selection, because natural selection changes the bell curve in a visible way that we can actually, there's visible ways that the bell curve can change that we can classify. So today we're going to learn the 3 kind of distinctive types of natural selection that can happen on a normally distributed trait. Now we're going to talk a fair amount about Galapagos finches in the near future, and that's cool. There's a adorable old couple, married couple, scientists that have been going to the Galapagos Islands for 50 years. Every year they go and they measure finch beaks and hang out with finches, and they've seen evolution like in action. Super cool. But right now, I don't think finch beaks is what we need. So we're going to use, I'm just going to make up some examples for you of these 3 types of selection. And we're going to start with aliens. For selection type 1, let's just kind of ride along with me in our science fiction story here. But the aliens get here, and it's not like we thought at all. They're horrifying. They're like, they can hover, and they're kind of like little birds, but they have razor sharp beaks, and they love eating people. Now, what saves us is they're pretty fragile, so they're only willing to get so close to the ground. In fact, they will only get 6 feet from the ground before they go like, no, danger, not going to get that close to the ground. And they'll hover at that level, and they will fly around faster than you can, basically faster than you can see, and absolutely wreak havoc, just eating heads all over the place, just slaughtering people. But they won't get closer than 6 feet. Who's in trouble? Who's in trouble? Yeah, those of us, 6 feet or taller. In other words, this part of the curve, right? This is the human height curve. This part of the curve's in trouble. Fast forward a few years. What has happened to this bell curve? Selene. This line? Yeah. It's still going to be a bell curve. It's just going to be a bell curve that's shifted this way, right? Because all the tall people got killed. That is called directional selection. When the critters at one end of a curve and the other end. Basically cause the curve to shift, can be left or right. And I would, if I were you, I would draw a simple curve here on the right just to represent that. All right, for the second example. Let's take a quick break from aliens. We'll come back to them. And let's talk babies. So, okay, let's first start with a really basic question. What makes us human? Good. I think, yeah, and I think we can agree that intelligence comes from what organ? Brains, yeah. And it's not a hard and fast rule, but typically a bigger brain is better. So we have these big fat brains. I mean, our crania are pretty intensely disproportioned if you look at a lot of other organisms, right? We got big heads. My question is this: how come they're not bigger? Wouldn't you think? I mean, okay, our neck can't support a bigger head. Well, it could if it had more muscles. Why this limit? Why do I have like one of the highest percentile head sizes? I do. It's huge. Why is that? Why didn't it get bigger? What do you suppose was the limit on head size in human evolution? Do you know? It's not what most people think.
Does it make them slower?
No, man, you would think a big enough brain, you could figure out a way to work around that.
Would it like get like the eyes or like other parts of like your skull?
Ooh, that's good. I like that. No, but you're getting warmer. No, blood flow is pretty flexible. You can oversupply kind of whatever you want. We already are, but yeah.
Like something to have to do with like the distance. If it's too big, there's like a higher distance from like back to it, like hard.
No. The answer is in, if you think about babies. You need to think about babies to get this answer.
Does this have anything to do with our
Mm-mm.
It's because of pregnancy, giving birth.
How so?
Because when the baby comes out, they come out head first.
Yeah, the head's the hardest part, right? Ask any mom. The head gets too big. It ain't happening. That's the limit. The hard limit on human brain size turns out to be the size of the birth canal. Although human evolution found a way around it for a while, they're bigger than they should be. You know how? No, that's now like, and C-section successfully really only happened with mom surviving for, a couple hundred years max, and evolution takes longer than that. But you're right that we've sort of short-circuited in that sense. But this came much earlier.
we're really close to
Sort of. They're already pretty big once they come out, but they do this trick.
And they like their skull.
It's ridiculous. It's so gross. Your skull didn't actually grow together until after you were born. Babies have their skulls in separate plates right up until after they are born. And so when you get born naturally, you basically, your head compresses into like a tube shape so it can get out of the birth canal. It's like it's why C-section babies look perfect, because they didn't have to do that. Whereas like a natural birthed baby looks like it just got in a big fight. Like they got a cone head and like all bruised up. Like, wow. It takes like 2 days for the head to kind of go back to normal round shape. Yeah. Because they went through, like a fun factory of life. So, okay, that's a limit here, right? Not big size, but like if you look at head size, that's a limit here. Baby birth weight, let's call it. They're selected against the really big ones because they don't come out right. And we can all agree that low birth weight isn't adaptive either, right? That's a problem. Low birth weight correlates with high mortality. So we're selecting against this end too. So what happens to the bell curve now?
ends are gonna,
Ooh, so it's gonna kind of come in a little bit?
yeah.
Yeah. But it's gonna basically stay in the same place. That kind of selection is called stabilizing selection, where the critters at each end, I'm sorry, where the critters in the center have the higher fitness. The curve narrows a little bit, the center might increase a little bit. Baby birth weight's a great example of it. So there's a baby on that graph. And again, I would draw that graph. All right, back to the aliens. Let's change the parameters just a touch. Let's say now, same deal, they can't get too close to the Earth, but really, actually, they're only going to be one height from the surface. They only hang out at about 4.5 feet above the surface. That's the only height they fly at. So they're zipping around the world faster than you can see. They're only about 4.5 feet above ground. And here's the other thing. They don't deal with bone very well. They really can only mess you up if they hit soft spots. Meaning, this is a problem, right? You're gonna plow right in there and wreak havoc. But here, they bounce off, maybe get injured, so they know better. Here, rib cage, they bounce off, get bruised, they know better. It's really only people whose necks are right about 4.5 feet. And that turns out to be right about in here, in the middle of the human height curve. So we're selecting against the middle now. And the ends are good. What's our curve going to do now? Okay, what's the middle of it going to look like? It's going to have a little dip in the middle. Yeah. This is the really interesting one. This kind of selection, which is called disruptive selection, where the extreme ends of the curve have the advantage. The middle is selected against. This can get real interesting if it happens long enough, consistently enough, over a period of time. Because here's the thing. If the middle of that curve is selected against strongly enough, if medium people just absolutely get slaughtered year after year after year, we could wind up with two separate curves, couldn't we? We could basically wind up with short people and tall people, no middle people. Then things start to get interesting because you know people. Do you know people well enough to realize that there might be some conflict there? That short people and tall people might have some issues, that there might be some, I think we could probably call it racism, right? Like, oh no, honey, you can't date him. He's tall. We don't date tall people, right? It's gross. Yeah, because yeah, could you see a situation where they kind of stop hanging out? Short people and tall people stop interacting with each other. Ooh, stop interbreeding. Oh, what's going on now, Amanda? I mean, that's kind of our definition, isn't it? Like two populations that can't or won't interbreed and produce fertile offspring, that's species. This is one mechanism that speciation can happen by. So 3 types, distinctive types of selection happening on a normal distribution. Here's some graphing to back that up, help you get it. Wait, a real example of speciation? Bunches. So we've seen a lot of birds do it. We've seen a lot of insects do it. It's tougher than longer lived species because it takes longer. But on the Galapagos, we've seen, well, the Grants, Peter and Rosemary Grant, have seen beak size get different enough that birds won't hang out with each other. Because the birds are real particular. Good examples of that. Okay, just to help solve any confusion here, understand that each of these 3 graphs you are going to draw is going to be a graph of number of snakes versus length of snake. I find that you're kind of programmed because you see time on here, 1980, 1984, and 1988. You're going to real bad. You're going to want to put time on the horizontal axis. Don't do that. That's not the right thing in this case. What you're going to do is you're going to put snake length on the horizontal axis. You're going to put number of snakes on the vertical, kind of like we did with height. But then you're going to draw 3 different lines on each set of axes, 1 line for each year. So what you're drawing is how the bell curve has changed between 1980, 1984, and 1988. So just make a little key. It's like, hey, a dashed line is 1980, a solid line is 1984, and a dotted line is 1988, something like that. And that way you'll kind of be able to see which type of selection is happening. The other thing I would say is that don't forget the box to the right. That's kind of where the money is there. That's kind of where you put your most important answers. So don't miss the box on the right of each of these graphs. Good? Otherwise, it should be easy. It is due tomorrow. Sorry, you don't have a ton of time to work.